I'm Mercurides, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 9. Find the unique Pythagorean triple a, b, and c such that the sum of the three variables is 1000, and print the product of the three. A Pythagorean triple is an ordered triple of positive integers a, b, and c such that a squared plus b squared is equal to c squared. We can jump right in and try writing some code. This week, we'll start drafting a solution in Perl. Perl is a very old scripting language, predating Python by 4 years and Ruby by 8, and serving as heavy inspiration for a lot of the string processing features of the latter. Perl was originally designed as a command-line scripting language, intended to replace and improve upon existing more special-purpose tooling, such as set and awk. It saw adoption more broadly as a CGI scripting language a few years later, and quickly cemented itself as the glue that holds a lot of software together. Let's get started. We have three variables, a, b, and c. In Perl, scalar variables are always written preceded by a $sign. We loop each variable from 1 to 1000 inclusive. Inside the loop, if the sum of the three variables is 1000, and the three form a Pythagorean triple, we know we've found our solution. In that case, we print the product and exit the program. Most modern Perl programs start with the same couple of directives. Being a language that's both old and widely used on the web, Perl has to go out of its way sometimes to maintain backward compatibility. This includes allowing certain early features that were, to put it bluntly, perhaps ill-advised, but which many programs now rely upon. Use strict is an assertion that your program does not rely on any of this awkward behavior, and allows the compiler to disable those features, instead producing an error which can help with debugging. For example, early versions of Perl featured what was called bare word poetry. Consider this simple program. We declare a basic function, or subroutine in Perl terminology, which returns the number 42. Then we call that function and assign the result to a local variable called x. In Perl, similar to Ruby, functions don't generally require parentheses unless needed for operator precedence or to make the meaning unambiguous. Finally, we print out the variable x. Simple enough, makes perfect sense. Now imagine that, as I was writing this program, my mind was mulling on something else, and I accidentally misspelled the function name. What do you think this program will print out? Is it A, the number 42, B, an error message, C, the string meaning of wife, or D, an undefined value? Think about it for a moment. If you said A, B, or D, you would be wrong. In default Perl without the use strict pragma, a bare word appearing in the code which is not the name of a function is treated as a string. Essentially, Perl simply pretends we had put quotes around the name and prints it out instead. For this reason and many others, use strict is generally a good idea to place at the top of any Perl program. Similarly, use warnings as like C++'s WALL command line option, which enables some basic common sense warnings, and is also a good idea in any modern Perl program. Finally, we declare 5.10 as our minimum Perl version. Perl 5.10 came out in 2007 and introduced several nice-to-have features and improved error messages, so it's generally a good starting point for a minimum declared version. Now this program runs, and in fact, produces a correct value in about 10 seconds. But you may already see some optimizations we can perform here. First, we know that A, B, and C have to add up to 1000. More precisely, if we know A and B, we can uniquely determine C without having to loop. This shaves off most of the 10 seconds, and this new program already runs instantaneously, but we can do even better. In Perl, next, as a key word, continues to the next iteration of the containing loop, similar to how continue works in C++ or Java. If C is not positive, then it's obviously not a part of a valid Pythagorean triple, so we can skip to the next loop iteration. However, our containing loop is for the variable b, and if we know C is too small, then that implies A plus B is already larger than 1000. So going back to the b loop and increasing the value of b won't help. In reality, we should be able to short-circuit all the way to the next iteration of the outer loop, which deals with A. In Perl, like in Java, we can give loops a name, and then when we use a control flow keyword like next, we can specify the name of the loop we wish to continue from. So in our case, we'll call the outermost loop outer, and direct our next statement to start from there. Finally, in a Pythagorean triple, the values A and B can, generally speaking, be switched. So without loss of generality, we can assume A is less than or equal to B. Now we have a working and efficient program. For reasons that will become clear in a moment, I'd like to make one more, possibly slightly unintuitive change. I'd like to flatten this nested loop into one single large while loop. Rather than looping over A and B separately, we have one big, ostensibly infinite loop. In the course of normal iteration, we increment B by 1. But if the sum of a and b becomes too large, then we instead increment a, reset b, and continue the loop from there. This is equivalent to our previous approach, but is written in a more convenient way for the loop we're going to write in a moment. Before we discuss the language of the week, we're going to take a brief detour and write a bit more Perl code. Let's write a program that takes an input n from the user, and then outputs the first n terms of the Fibonacci sequence. The Fibonacci sequence has come up in previous challenges. It begins with two terms, 1 and 2. Then each subsequent term is calculated as the sum of the previous two terms in the sequence. We don't actually need this for problem number 9, but will serve as a good example program in just a few minutes. We begin with our three use pragmas. Then we declare three variables, count a and b. The variables a and b will store the last two Fibonacci numbers, and the variable count will store the number of times we wish to iterate. A and b are simply initialized to 1 and 2, and count is initialized to, of course, a diamond. This less than greater than sequence in Perl is colloquially called the diamond operator. The diamond operator is a special sort of do-what-I-mean operator in Perl. If our program is started with no command line arguments, then it reads a line of input from standard input. If our program does have command line arguments, then it regards each of them as a file name and reads from those files in order instead. This mimics the behavior of a lot of built-in Linux utilities. For instance, the built-in sort command on Linux can be called in one of two ways. If given one or more arguments, it will read in all of the arguments as files, and then sort the lines of those files into one big sorted list. However, if given no arguments, then it will read from standard input until it hits the end, and sort those lines instead. This allows utilities like sort to be used on their own, or as part of a pipe of shell commands conveniently. Back to our program, we iterate over the range from 1 to count, inclusive. We could have given our loop variable a name like I, but we don't actually need it, so we can omit it entirely. Inside our loop, we print a, then update our Fibonacci variables using the same sort of parallel assignment trick you often see in Ruby and Python. Now, we'll get back to this Fibonacci program in a few minutes, but first, let's talk about the language of the week. Welcome to the Shakespeare programming language. In this language, as the name implies, we'll be writing our programs in the form of Shakespearean dramas. Shakespeare is a well-known example of a pseudo-natural programming language. What that means is that our source code is going to somewhat resemble natural English text. Rather than writing if statements in some made-up syntax, we'll use plain English sentences in a specific form, so that the end result to the untrained eye looks like ordinary prose. Broadly speaking, a Shakespeare program is split into three parts: a title, character introductions, and the acts of the drama itself. To see an example of all of this, we'll work with a simple program that takes two integers from the user, sums them, and then prints the sum. Every Shakespeare program begins with a title. The title doesn't actually affect the program, and merely serves as an indicator to the reader of its purpose. After the title, we introduce the characters who will act in our play. The characters are going to serve as our variables. Each character we introduce in this way is capable of storing a single integer value. Our characters, naturally, must be named after actual characters in Shakespeare's plays. We'll use Hamlet and Horatio in this example. Each character starts with a numerical value of 0. Once again, the brief description of each character has no actual bearing on the program. Finally, the actual instructions of our program take the form of acts. A Shakespeare program consists of one or more acts numbered by Roman numerals. Each act, in turn, contains one or more scenes, likewise indexed by Roman numerals. The program begins in scene 1 of Act 1 and continues linearly through the code. The actual act and scene numbers will serve as labels, which can be the target of conditional statements, but we'll get back to that in a moment. Our actual program proceeds on a stage. On this stage, there are at most two characters at a time. To instruct a character to enter the stage, we place the command enter in brackets. To instruct a character to exit the stage, we place the command exit in brackets, or exeunt if we wish for multiple characters to exit simultaneously. Characters execute instructions and perform arithmetic by talking to each other. Our play will begin with Hamlet telling Horatio to listen to your heart. This instructs Horatio to take one input from the user as a number and remember it as his current value. Note that in Shakespeare, characters never instruct themselves to perform actions. If we want Horatio to do something, we have to have someone else, Hamlet in our case, enter the stage and tell him what to do. In our case, we want to take two inputs, so we'll have Horatio issue the exact same instruction to Hamlet immediately afterwards. Next, Hamlet will issue two instructions to Horatio. Since it's the same character talking, we can issue both instructions on the same line. First, we do some arithmetic. A character can tell another character what their numerical value is by comparing them to something, in this case using a simile. In our case, Hamlet tells Horatio that he is as bold as the sum of the two characters in our play. This sums the two numerical values and stores the result in Horatio. Finally, Hamlet tells Horatio to open his heart. This instructs Horatio to print out, as a number, the value he's currently storing, which is the sum of the two inputs. We terminate our program by having the actors exit the stage together. Now let's do something a bit more non-trivial in Shakespeare. Let's take our Fibonacci sequence program we wrote in Perl and translate it into Shakespeare. More specifically, let's take a slight modification of our Fibonacci program and translate it into Shakespeare. Since Shakespeare doesn't have an easy way to swap variables, we'll use a temporary variable to do our swap inside of the loop. Let's get started. We'll call our play, fittingly, the Fibonacci sequence. Our Perl program had 4 variables, A, B, count, and temporary. So we'll need 4 characters. A and B will correspond to Romeo and Juliet, count will be represented by Ulysses, and our temporary variable will be represented by Sebastian. Our program is fairly small, so we'll only have one act called the Fibonacci values. The first scene of this act will set up our variables. Romeo's initial value should be 1, Juliet's should be 2, and Ulysses should get input from the user. Sebastian needn't appear in scene 1, since he'll only be used for temporary work inside of our eventual loop. First, we introduce Romeo and Juliet. Constant values in Shakespeare are indicated by a noun preceded by 0 or more adjectives. There's a list of the nouns and adjectives that are accepted by Shakespeare, and they're mostly the sorts of words you'd expect to find in a Shakespearean play, with a few cute Easter eggs thrown in. The value of a noun is indicated by its tone. A positive noun, such as king, angel, or flower, has the value +1. A negative noun, such as curse, devil, or leech, has the value -1. Then, each adjective preceding the noun doubles its value, regardless of whether the adjective is positive or negative. This allows us to produce any positive or negative powers of 2, and to produce other numbers, we simply do arithmetic on those values. For example, king is a positive word, so it gets a numerical value of 1. A cunning king would have a numerical value of 2, and a gentle cunning king would have a numerical value of 4. Similarly, a fat dirty king would have a numerical value of 4, since although the adjectives are negative, the initial noun is still a positive word. On the other hand, a devil would have a numerical value of -1, while a red devil would have a numerical value of -2, a small red devil, -4, and so on. In our case, we want Romeo to have the numerical value of 1, and Juliet to have the numerical value of 2. So Romeo will call Juliet a beautiful angel, and Juliet will compare Romeo to the sky. Once Romeo and Juliet are done complimenting each other, Juliet will leave so Romeo can talk to Ulysses. Romeo will simply instruct him to listen to his heart, which instructs Ulysses to take numerical input from the user. Now we'll proceed to Scene 2. Scene 2 will make up our for loop, effectively. The first thing we'll do is decrement Ulysses, who is still on the stage from Scene 1. At the end of this scene, we'll do a check to make sure Ulysses is bigger than 0, and exit when he's not. As we've already seen, to add 2 numbers together, we have a character compare someone else to the sum of 2 things. In this case, we want to decrement Ulysses. So we want to add Ulysses' current value to -1. We need a negative noun. We have a lot of options, such as devil, coward, pig, and bigger. But I find it particularly amusing that this implementation of Shakespeare considers Microsoft to be a negative noun. So I think it's entirely in character for Romeo to compare Ulysses to Microsoft. Next, we'll enter Sebastian, our temporary variable. Sebastian is going to instruct Romeo to open his heart, printing his current numerical value to the screen. Then Romeo is going to tell Sebastian several things. First, the open your heart instruction doesn't print a new line. So we're going to print a new line using Sebastian. We need him to have the numerical value 10, which is the ASCII value for the line feed character. So we'll have Romeo build up the number 10 as the sum of a rich lord, whose value is 2, and an amazing, noble, peaceful king, whose value is 8. Then we'll have Sebastian speak his mind, whereas the directive speak your heart prints out the current value of a character as a number, speak your mind prints out the current value of a single character using the ASCII encoding. Since Sebastian has the numerical value 10, he'll print out the character with ASCII value 10, the line feed. Finally, we set Sebastian to Romeo's current value, using him as a temporary variable, just like we did in Perl. Sebastian exits the scene and Juliet enters. In a moment of sudden narcissism, she decides to remind everyone that she's sweet, setting Romeo's value to her own. Then Romeo exits and Sebastian re-enters. Sebastian sets Juliet to the sum of both of them and both characters exit. This is the end of our loop. Now we need to do a check and see if Ulysses' value has dropped below 1. If so, we'll end our program. First, we instruct Romeo and Ulysses to enter. It didn't have to be Romeo, we just need someone to talk to Ulysses. Comparisons are done by cooperation between 2 characters. One character shouts a question and the other makes a comment as to what to do about it. In our case, the comparison we want to check should be the question, is Ulysses less than 1? Remember that +1 is the numerical value of any positive noun, so Ulysses will shout, am I smaller than an angel? Which sets up the comparison. Then Romeo indicates that if the conditional is false, that is, if the value of Ulysses is greater than or equal to 1, then we should return to scene 2, repeating the loop. On the other hand, if Ulysses is less than 1, we don't do a jump and instead continue to the next instruction. In our case, there is no next instruction, so the program merely terminates. It's important to note that this language is actually not that weird semantically. There's no hexagon grid we have to keep track of, no infinite tape of memory, or complicated ways to print out numerical values. Semantically, the language really is just arithmetic, variables, and some basic go-to states. The interesting part of the Shakespeare programming language is the pseudo-natural syntax, designed to read like a Shakespearean play. Alright, let's write our real program. This Perl program has 3 variables, A, B, and C. We'll call those variables, respectively, Romeo, Juliet, and Hamlet. We'll also use Julius Caesar and Ophelia as temporary variables in a couple places to store intermediate calculations when we need to do comparisons. Finally, to avoid having to chain so many adjectives together all the time, we'll store the number 1000 in Oberon and use him as a constant. That makes 6 total variables for our program. Let's get started. We start in Act 1, Scene 1. We need to initialize some variables. We'll have Caesar set up everyone's values. First, Romeo enters, and Caesar calls him a chihuahua. This is, of course, a positive noun, so Romeo takes on the numerical value of 1. Then Juliet enters, and Caesar feels a bit more loquacious. He compares Juliet favorably to a mistletoe, another positive noun, setting her value to 1 as well. Finally, Oberon enters. We want to give Oberon the numerical value of 1000. Remember that the only constants in Shakespeare are powers of 2, so to produce the number 1000, we'll produce 32, square it, then subtract 24, which is 16 plus 8. To do that, Caesar needs to pile some heavy compliments on Oberon. It's just a bit of arithmetic to produce the number we need. Now we move on to Scene 2. Scenes 2 and 3 will collectively make up the main loop for our program. We'll use Scene 2 in the situations where we need to update Juliet's value, and we'll jump to Scene 3, then back to Scene 2 when we need to update Romeo. Now inside of our main loop, we tell all cast members to exit the stage. Exeunt without names simply instructs all characters present to exit the stage immediately. Now we're going to add A and B, or Romeo and Juliet, together to determine if that value is greater than or equal to 1000. If so, we need to increment Romeo in Scene 3. To do that, we take Caesar and set him equal to the sum of Romeo and Juliet. We do this in 2 steps. Then we bring Oberon, who stores the constant value 1000, onto the stage and have Caesar compare himself to Oberon. If Caesar is greater than or equal to Oberon, we move to Scene 3, where we'll update Romeo. Otherwise, we need to check and see if this set of A, B, and C, or Romeo, Juliet, and Hamlet, is a Pythagorean triplet. First, we need to calculate Hamlet's value, which we'll do by taking Oberon and subtracting Caesar. Oberon has value 1000, and Caesar is the sum of Romeo and Juliet. So Hamlet is the unique value who, when summed with Romeo and Juliet, will equal 1000. Next, we perform the actual check to see if a squared plus b squared equals c squared. We'll store a squared plus b squared in Caesar and c squared in Ophelia. This just requires a bit of shuffling the characters around to get them to perform the required arithmetic. Once we've set up our characters, we need Julius Caesar to ask if he's equal to Ophelia. If so, then we've found our answer and we can proceed to Act 2, where we'll print out the result and then terminate our program. If not, then we have Caesar pay Juliet a compliment to increase her numerical value by 1, and then return unconditionally to the beginning of Scene 2. Now on to Scene 3. Scene 3 is where we go if the sum of Romeo and Juliet has exceeded 1000. In this case, we need to increment Romeo and reset Juliet. So we'll call this scene Romeo's Training. In Romeo's Training, Caesar pays Romeo a compliment to increment him, then Romeo sets Juliet equal to himself. Finally, we return unconditionally to Scene 2 and repeat our main loop. Act 2 will trigger when we've found our answer. At this point, Romeo, Juliet, and Hamlet contain our A, B, and C values. We need their product, which we'll store in Ophelia. We have Ophelia enter the stage, and our 3 main characters enter in order and complement her, in order to multiply her by themselves. Finally, Oberon enters the stage and declares that Ophelia should open her heart and cry out the correct answer, ending the program. And this solves Project Euler problem number 9 in the Shakespeare programming language. Tune in next time when we take a look at the 10th problem in CJam, a stack-based golfing language heavily inspired by GolfScript.